Okay, welcome back to the classroom. My name is Mr. Wong. We are looking at Kepler's laws of planetary motion, but for this particular recording, we're actually looking at doing some calculations related to Kepler's law instead of looking at the theory. So let's get started. Now, just a quick refresher of how we derived Kepler's law using Newton's law as well. We firstly stated that in order for a satellite to rotate around a planet, its centripetal force was contributed by the gravitational force of the larger object of that particular mass. We did our substitutions and we got this formula here. If we rooted it on both sides, we'd get the orbital velocity of the small object moving around the larger object. But if we substituted v square with 2 pi r over t, which is the tangential velocity of a satellite moving around a larger object, we would get the following equation, which is just a nice little reflection on Kepler's third law of motion. And then we talked about the different types of formulas we could obtain using Kepler's period laws. So let's start off with doing some calculation questions. Let's compare the period of orbit between two satellites orbiting the Earth, one at an altitude of 250 kilometers, the other at 40,000 kilometers. So going through the first calculation, we just simply have it like so. You could rearrange all the numbers first. What I will do though is actually substitute my values in, and then we'll go from there. Okay, so firstly, our radius is at 3.38 times 10 to the power of 6. That's the radius from the center of the Earth to the surface, plus the altitude of 250 times 10 to the power of 3. Again, we're converting this into meters cube over our period, which is what we're trying to find. G is 6.67 10 to the power of 11 times the mass of our planet divided by 4 pi. Okay, 4 pi squared. So what we need to do is rearrange to make t the subject of the equation. So simply what would end up happening, it would look something along the lines of this. So it become t to the root of our radius. Okay, so our radius cubed times 4 pi square times the gravitational constant times the mass of our planet. And that gives us a period of approximately 5,380 seconds. So that's how you do that. You do the exact same calculation for question B, and you would get a value of that sort as well. Okay, we might also show that one as well. So I'll just get rid of some of these numbers. The working out is essentially the same. You're just swapping over some numbers. Okay, so we have the average radius of our planet plus the altitude that we're dealing with. And we would end up getting a orbital period of about 99,500 seconds. And that's how you do this first question here. Okay, now we can move on and we can look at applying Kepler's law on Mars. So what we want to find is the orbital constant for Mars. So essentially the orbital constant is uh, r cubed over t squared. Okay, so our constant, let's just call our constant k, give it a notion like that. We have the gravitational constant, the mass of Mars, okay, and then we have 4 pi squared. This gives us an answer of approximately 1.11 10 to the power of 12. And then we go to question B. It says find the orbital radius of a satellite orbiting Mars, as you can see here. So using the same formula, okay, so squared gm over 4 pi squared. So the rearranged equation should be r cubed times t squared, then get rid of the cube, it'd be cube root for this particular answer here. Okay, so that's how you do that one. So if we were to rewrite this equation, be 11 10 to the power of 12 times the orbital period, which is 1.6 times the power of 3 square. That gives us an approximate radius of 121,000 meters. And then we have question C, find the period of Mars satellite when its orbital radius is this particular value here. Okay, so this satellite up here, they both orbit Mars. So you have two satellites. So you have Mars here, one satellite's here, other satellites here. So they're probably at a different radius, but their orbital constant would be the same as each other. So if I rearrange my equation, it looks like so. Pi square divided by gm. Okay, so if we do our substitution, it'd be 2.58 times 10 to the power of 7 cubed times 4 pi square over the gravitational constant times the mass of Mars. And we can actually use the ratio or the constant that we used earlier because it's two satellites orbiting, don't forget. And that gives us a orbital period of approximately 1,000 or 125,000 seconds. Okay, let's go to question 3. Okay, so we have a small planet observed to obtain a star every 30 days. A second planet orbits the same star at a distance that is 9 times the orbital radius of the first planet. What is the period of the second planet? So we can use this ratio here. If you want, you can label these components to help you out. So it would be T2 is equal to the square root of, let's see, what do we have? Our second radius cube times T1 squared over R1 cube. Okay, if we do our little calculations here, you can see 9 R1 cube, because R2 is 9 times the amount in orbital radius than R1. So we can write that. 30 days, and then R1 cube there. These can cancel each other out, so that cancels out with that. We still have the cube on the 9, so we end up with 810 days. Okay. Determine the orbital speed of the moon, assuming it has a circular radius of that around the Earth, and take the mass of Earth as following. So, we can rewrite the equation like so, because we know that gravitational acceleration can be expressed like this, particularly if it's in circular motion. So, we can find the orbital radius, or orbital velocity. Okay, and we get the following value here. That's a 3 there. And you find that you'll get a velocity of approximately 1.02 times 10 to the power 3 meters per second. Okay, so that's question 3 and 4. And we'll go to our last question. Okay, Gatamine is the largest of Jupiter's moons. It has a mass of that. It has an orbital radius of that value and an orbital period of that. Use Kepler's third law to calculate the orbital radius of Europa, another moon of Jupiter, which has an orbital period of 3.5 days. So we can equate the equation like so, where this is Gatamine, this is Europa, or however you want to write it. So the formula to express it, it'd be Re equals to the cube of Rg cubed divided by t squared times t of Europa gives us that. If you substitute all those values in, you should find it is about 6.71 10 to the power 6 kilometers long. Next one is the orbital data for Gatamine to calculate the mass of Jupiter. So in order to calculate the mass of Jupiter, we're using the following formula. So we have Kepler's formula. You can find that the mass is equal to 4 pi squared times R3 over GT squared. Now, obviously this one here, I've just rearranged the equation around. So you could do that, or you could select otherwise. And if I do those substitutions there, I'll find that the mass of Jupiter is about 1.9 10 to the power 27 kg. If I then want to find the orbital velocity, V equals to gm over r. You already know what the gravitational constant is here, and you already know what the mass of Jupiter is, divided by the radius, which we found a bit earlier, and also the radius of Jupiter. So we have 991 10 to the power 3 plus the radius of the orbit, which is 1.07 10 to the power 9, and that gives us a orbital radius of about 105 meters per second. Okay, and that concludes our lesson for today. So we went through Kepler's laws, and this recording we went through the calculations in order to answer those questions. Now there's a couple of exam paper questions that you can look into. Some links will be available for you. Anyhow, Thank you for joining. If you found this video useful, give it a like and subscribe if you haven't done so already, and I'll see you next time.